Hello guys, let's look at next topic, sequences and summations. Now this topic I'm going to go over very quickly because for us it is really something, just a little bit of more objects that we can use in our analysis, in our next discussions on discrete math, but especially in discrete math 2 this will be much more studied, sequences and summation. So that's why I don't want to say too much about it. A sequence, what is a sequence? Well, that's just a list of numbers indexed by an index, and the index normally runs from 0, 1, 3, etc. But sometimes you can have a sequence that starts from a different number, except from 2, but that's not even, it doesn't even have to start from 1, from 0 or 1, it could start from 7 onwards. Right, it just depends on the typical situation that you're in. And these are just a bunch of numbers. So these are real numbers for us. Remember, we can now write this with our notation like that. And so these are objects that we like to study because they are somehow, this is part of discrete math, because this is like, what is the difference of a sequence and, for instance, an actual function? In the same thing that we see in a sequence is a function, really, right? You can think of this as a function in terms of n. So where a is a function that sends a natural number to a real number. So a sequence is really just a function from natural numbers to the real numbers. Often these are not real numbers; they could actually be fractions or even just natural numbers. So, but and in fact, it doesn't even have to be numbers. You'll see sometimes we have sequences of names, sequences of, I don't know, social security numbers, or anything we can start listing, or sequence of words, something like that. It depends on what kind of database we're looking. So you can think of these also as the elements in the database that are ordered. Okay. So that's what a sequence is. And we normally have either a rule that tells us how this sequence is built, or we have a formula that actually tells us how to calculate it, or we just have a sequence that is built up by, as I said, for instance, if you would put, what is a dictionary? A dictionary is a sequence of words, of English words, presumably all English words, and it's listed alphabetically. So there's the first word and the second word and the third word in the dictionary, and that would give you a sequence. Okay, so that is no actual formula for it. You really need to know the English language to figure out what this sequence is. Okay, so there are two sequences that appear a lot. So I'm going to quickly geometric sequence. The geometric sequence is a sequence where we have a fixed ratio r. So r is the ratio. I'm going to write capital R here. Which means that to figure out the next number in the sequence, you just multiply the previous number with r. And so that would be, if we start with a, so if a0 is a, what would a1 then be? Well, I have to multiply that with r. Okay. And what is the next one? Well, I multiply that again with r. So ar times r, that is ar squared, right? And I will keep doing this. So a3, what is that? Ar cubed, right? So you see that there's a pattern here, and so we say an is a times r to the n. Now the pattern that we recognize is that this exponent is the same as this index, and so we postulate here the general formula. Now we can prove this, but the proof of that requires a method of proof that is called induction. We will study at the end of the course. But in discrete math 2, we will study a lot these kind of things, similar things like that. So, and you might also have seen this in Calc 2 already. Geometric sequence and series are studied there too. Okay. There's another one that is called the arithmetic sequence, and it has the same kind of rule, except instead of multiplying, we add, and this we call that the common. So this is sometimes the common ratio, and this is called the common difference. So what it is to find the next number, you just add d to the previous number. So again, if we start with as number a, so we can start with any number a here. So a can be any number, but once we choose that number, everything else is fixed, right? Because a1 is now, we have to add d to this thing. So no more choice here. What is a2? Well, we have to add d to that. So a plus d plus d. Well, that's a plus 2d, right? And what is the next one? a3. I hope everybody sees it's 3D. So again, we see a pattern, right, that this factor here is the same as this index. And so the general formula will again be an is a plus dn. And this can be proven, but we are not interested in the proof here. That's because, for one thing, we don't know yet proofs by induction. So I'm not going to say much more about that then. There's another type. See, what is going on here is, in both cases, we found the next number from the previous one. And this is a principle where you calculate the next from the previous. This is called recursion. So recursion, recurring, the same thing keeps recurring over and over, but what it means is a recursion is where a sequence, an, or an plus 1, is determined by a rule about the previous element. And it might even be that it's not just the previous, but the last two elements, or the last three elements. Okay, so let me give you an example. So this would be an example of a recurrence relation. An plus 1 is r times an. The previous one, an, you multiply that with r and you get the next one. So this is what we call a recursion relation or recurrence relation. And it tells us that we actually can build a sequence knowing from the previous sequence. Another way of saying that is, and we'll come to that shortly, is that we can use a program in which, so what are the sequences then? If you think of programming, and I said we'll look at it shortly, is that we have a loop, a do loop, where a certain variable, an index, loops from some number to another number, and you carry out some calculations, and it is very common in programs to calculate a value from the previous value. Okay, and that is exactly what recursion is called, recursive relation. And by the way, which is this? It's exactly what the rule for geometric sequence, right? This is exactly what I said the geometric sequence would be. Namely, take the previous one, multiply with r, you get the next one. Now, you might ask, how do you previous the next one? How do you write that down? Well, exactly. That is what does the next one mean? Well, you take this index, and the next one is the number with index 1 higher. So sometimes we write it that way. Sometimes this is the same content, so logically equivalent is to write it this way, because it is still the same thing, right? The previous one, this is with index n minus 1. What's the next one? Well, the one with one higher index, that would be n. So the content of this and this is the same. And sometimes it depends on the situation. We write it this way or we write it that way. So this is called reordering a sequence. You can we remember what we're doing. As I said, it is an ordered list of numbers, ordered by the zeroth one. It's a bit weird that we start with 0. So therefore, sometimes we start with 1, the first one, the second one, the third one. But we can reshift this a little bit and say, okay, I want to start not from 1, I want to start from 0. So what I called a B1, I'm going to call now A0, and B2 becomes A1, and so on. I shift the index by 1. And this kind of shifting is what we see here as well. Okay, this is recursion. I'm going to give you one example of a recursion relation, and that is a very famous one. This is called the Fibonacci. Fibonacci, I always have to think about the correct spelling of this, so give me a sec here. I don't want to write it wrong. Where is Mr. Fibonacci? It's with 2. Yes. So there is a double consonant here, and it's the last one. Fibonacci sequence. It's the name of a person, an Italian mathematician, and so what is a Fibonacci sequence? It is given by the following rule. Fn is, so it is again a recursion rule, so it says how it depends on the previous one, but it's actually not just on the previous, on the two last ones. So the one with index n minus 1 and one with index n minus 2. Now, if you remember, even with the geometric sequence here, in order to actually calculate the geometric series, so let's do a really example, right? Suppose that r is 2, and A is 5. Let's calculate some of the values. A0 would be, well, that's the initial condition here. A0 is 5. So then A1 would be double this. This means doubling, right? So 10. And A2 would be 20. And A3 would be 40. And so on and so forth. Okay? So it is clear that if we want to do this, we need to know what the start is here. That's why I call it initial condition. We need to start somewhere, and the same here we had from the arithmetic sequence. Therefore, any recursion relations, you need to know where to start. And if you need the previous, so suppose I want to calculate, okay, so what is, I need to start somewhere. So let's call F0, let's see. F0 I call just 0. But is that enough to start? No, because if I want to calculate F1, well, that would be depend on the previous two ones. That is F0, and then what's the one before F0? We normally don't allow negative indices, so that doesn't work at all. So this I cannot do this. I need also F1 I cannot calculate, so I need to know what F1 is. And okay, let's say F1 is 1. This is what in the Fibonacci sequence happens. But now I can do everything. See. And so if F is 2 here, let's calculate F2. Well, by this formula, that would be F1 plus F0. Well, that is 0 plus 1, 1 plus 0. Let me write it in the right order. That is 1. Okay, nothing fancy is happening here. Let me move this a little bit. We'll need this later, but I want to get it out of the way. Okay, so what is F3 now? So by the formula, it is a formula, but just think of it as a recipe. The recipe says take the previous two ones. So the previous one was F2, and the one before that was F1, and we know the values. F2 was 1, and F1 was also 1. That was given to us, and this one we calculated. So F3 is 2. And now we can calculate F4. That would be F3 plus F2. F3 is 2, F2 is 1, so I get 3. And so we can, let's list the Fibonacci sequence, so Fn. So the first one was 0, right? Then we had 1, then another 1, then we had 2, then we had 3. So what will be the next one be? It's even easier to just write them down. Well, we take the last two ones that we enlist and add them, and you get 5. And then what's the next one? The last two, add them, 8, and that's the next one. What's the next one? 13, right? We add these two and we get that. So each time we adding here, each time adding. So 21, 34, etc., etc. Now, okay, just you might say, okay, cute. It's more than cute. It's kind of the Fibonacci sequence for something we perhaps still not fully understand, occurs a lot, not just in mathematics, but also in physics, in economy, even in biology. That is a lot of processes are built on this principle, the Fibonacci sequence principle. And also there are formulas for the Fibonacci sequence which you will all derive in discrete math 2. So this is a commercial for the discrete math 2 because it's very interesting. Once you get a formula for these things, and they are very interesting formulas, not what you would expect. And they involve, for instance, for whoever knows what it is, the golden ratio, which is an important concept in architecture that gives you what is the most pleasing ratio between the height of a building and its width. And for some reason, and perhaps that's the reason why it's so the Fibonacci sequence occurs so lot in nature, is because the golden ratio occurs a lot in nature. Plants, flowers, patterns of growth all have the same golden ratio somehow built in. It somehow is evolution has found that as one of the best ways of constructing nature. I cannot say much more about it. It's a fascinating topic on its own, but just be aware that this Fibonacci sequence. There's a reason that we have given a name, that we honor this mathematician Fibonacci from the Italian from the long time ago, because it's such an important sequence. Now, okay, I want to skip a little bit what is done next, and I want to go to summations. There's more in the textbook, and so please read it a little bit more about these Fibonacci sequences and other interesting recursive functions and relations and so on, and how to solve them, but I'm not going to go there. As I said, I want to go rather quickly. So what is a summation now? Well, when you have a sequence, you can add them up. Okay, it's different than the recurrence relation, right? Here we would adding the last two. But what if we have this sequence here? So let's just get rid of all these ornaments here. And if I now ask, okay, let's take the sum of the first 7 of these numbers. What would you do? Well, 1, 2, 3, 4, 5, 6, 7. These are the 7, and just add them up. Okay, that would in this case be 2, 4, 7, 12, 20. So the sum is 20. And if I would add up, that's the first 7. If I would do the first 8, I would have to add 13, and so on. So this is the principle of adding a bunch of numbers starting from the beginning and go up till a certain range. We're going to only do finite sums. If you want to do infinite sums, then you have to go to calculus, and then they're called series. But for us, we do finite things. But we want to have a notation for that. And the notation is this Greek letter. It's a capital Greek letter sigma, which sigma is the equivalent of our S, and it looks also rather like our S. By the way, that's how our current Roman letter S comes from the Greek, or is modeled on the Greek letter S for sum. But it has 2 parts. It has 3 parts actually. It says it has an index, and it says where the index starts and where the index ends, and the index is then also used to describe the sequence that you're going to add. So in this case it was the Fibonacci sequence, so let me use the letter F here, and I said the first 7, right? So this is formally writing down what I said. Take the first 7 elements of the Fibonacci sequence and add them. Okay, so I could do the same thing. Let's say, let's add the first, so okay, notice that I started from 1 here. I should have started from 0, right? Because, right. Okay, sorry. This is actually a little subtlety that I myself made a little mistake too. The first 7, but computer scientists and mathematicians like to start from 0. So the first 7, so let's see, what are they? So this was F0, this was F0, this was F1, this was F2, F3, F4, F5, F6. The first 7 actually is only going up to 6 here. So I actually wrote this wrong. What I wrote down, so I can, what did I write down? What I wrote down is this part, adding these guys, that would be given by this blue guy, right? You see the difference between that and this, which is the green guy, which would have we calculate as 20. These are the first 7, and this is something we're going to run into sometimes problems, because when we start from 0, what is this, the first one is then the 0th one. That's kind of weird, and the second one is the first number 1. Okay, so we're going to have to be a bit careful when we talk about indices like that. So okay, the blue one. What's the blue one then? Well, the blue one is we have to add the F1 up to F7, and that would actually be, so Fi, that would be 33. Agree with that? Okay. So, for instance, I can do now, so again, let's start from I from 0 to 5, say, and I want to calculate the geometric series, AI. So AI is the geometric series with ratio 2 and initial condition 3. Okay, so what would that be? Well, let's write them up. This is A0 plus A1 plus A2 plus A3 plus A4 plus A5. What is A0? Well, that is the initial term, 3. And that A1 is just obtained by multiplying with a fixed ratio, in other words, doubling. 6 plus 12 plus 24 plus 48. 1, 2, 3, 4, 5, and one more, right? I go up to 5, that's actually 6 that I'm calculating therefore. And so doubling that one is 96. And now we have to add them. It gets already, okay, we can add them. I'm not going to even do that because we have formulas for these things. And so that's what this little table is here. The first formula, we'll talk about the other ones later, but let's look at the first formula here, this one. Notice here we have the ratio r, which is written in small r. Of course, it cannot be 0. And little a, that is my initial constant. Notice that there is a problem if r is 1. Because in this formula, because if r is 1, what happens then? That then you don't do anything, right? It's the constants. If you multiply each time with 1, you don't do anything. So it's a boring sequence. It's a sequence that always is a. So there's no need to find that out here. So according to this formula, let's use the formula here. So this would be equal to a times r. I'm going to write the formula. 1 higher than, look at this. Here is n, and here is n plus 1. That is how the upper bound plays. The upper bound plays here comes in this way. So I have to write here n plus 1. Okay, they write it this way. I'm going to write it this way because it's really how people normally write this. Okay, so let's work this out. A was 3, r was 2, n was 5, so this is 2 to the 6th minus 1 divided by 2 minus 1. Oh, that's nice, that's just 1. So this value is equal to 3 times 2 to the 6th, that is 64, minus 1 is 63. So it's 3 times 63, that is 180, 189. And so I challenge you to actually calculate this thing, and you will see it is actually 189. So what we're going to do is when we have summations like that, we are going to use these formulas here. And oh, this is circled from a picture. Sorry, I cannot undo that. Okay, and so we see here a couple of other formulas, the only ones that I'm interested in. So I'm gonna, the one we're gonna mostly use, I'm gonna kind of do this way because we're not gonna use them that much. So the ones here, the sum of the first n numbers. This is the sum of the first n numbers given by this formula. The sum of the first squares is given by this number, and the sum of the first cubes is given by this number. Okay, that's just. And so this is an application here, and this is also. Let's do this here. Let's use, for instance, the sum of the first n numbers. So k going from 7 to 90. Okay. Okay. I want to calculate this using the tables, but there's something that we have to pay attention to. Let's see. The table, what we have in the table is the upper bound, n. We know what the upper bound is here, 90. So our n is 90 here. But are we in the case of the table? No, because in the table you have to start from 1 and we start from 7. Okay, so in other words, what I'm saying is if we would have to calculate this guy, then I can use the table. By the table, this is equal, my n is now 90, and I plug it into this formula, and I get 90 times 91 divided by 2. That is 45 times 91. I'm not going to risk doing this in my head because for some reason I am not sharp today. Times, sorry, that's wrong. 91 times 45, that is 4095. But that's not what we want. What are we calculating here too much, right? So here, if we would symbolically think of this as a loop, for this thing, k will go from 7 all the way to 90. So, okay, let's think that it's not I don't mean to say a function here. I mean to say let's write it like this. We go from 7 to 90 by steps of 1. That's how we loop. Here we go from 1 to 90, right? Or k goes from 1 to 90. So this we know, this we still don't know. Now what is the difference between is that this one we can split this in two parts. We can go from 1 to 6, and then from 7 to, sorry, I got a little bit in the way here. Let me do this over again. So, okay, we go from 1 to 90. Let me just do it this way. And I can split this in two parts. We go from 1 to 6, and then we go from 7 to 90. Okay? What is it that we want? Let's see. We want this part, 7 to 90. So that's what we want. What we have calculated from 1 to 90, this part. Yeah, so it comes down to the same thing. So what it is that we have to do is we calculate too much, so we have to subtract. What do we have to subtract? This one. But that one I also have a formula for. What is this? This is the sum, okay, going from 1 to 6. The first 6 numbers, and now we see that here we have the formula where n is 6. So I plug this in again, I get 6 times 7 divided by 2, that is 42 divided by 2, that's 21. So in conclusion, the sum going from 7 to 90 of all the case is equal to, it's the sum going from 1 to 90, and then we counted too much, so we subtract what we counted. If you want, this is kind of inclusion-exclusion principle again. We go from 1 to 6, be careful, right? The last one I won't want to count is 6. I do want to count 7, so I should not subtract it. So that's why I go up to 6 here. You understand this? Okay, so be careful, right? Here we go from 7 to 90. If I go from 1 to 90, then I should not count from 1 to 6. That's what it says. And we calculated each of these values. This one by the formula was 4095, and this one was 21. So the actual value is 4074. Okay, that's how you use these tables. I'll do some homework problems on that. And then one more thing. Sometimes what we use is double summations. So let me do just an example here. Suppose we have to do summation from I going from 1 to 2, and then a summation from j going from 1 to 3, and we will do I plus j. So what we see now is that we have one summation. If you think of summations as, again, we're going to go there very short in the next videos, is that to calculate summations like this, to calculate summations like this, you can write a program where you let I really be the variable in a loop, and you loop from 0 to 5, and you just keep adding your number. We'll see how to do this. So you can think of this is one loop where the index is indexed by I, and inside that loop we have what we call a nested loop, a new loop where we go from j from 1 to 3. And then we have an expression that we calculate, and we have to, now this sigma means sum, right? Sigma, capital S, means summation. So how would this work? How would you work this out? I find it easiest to make a table here where I really look basically at all the different states. If you would write this as a program, which as I said we will do shortly in a different video, then I make all the different states that my loops are in. Namely, what is this happening? My first index can either be 1 or 2, but I cannot just say 1 and then 2 here, because I also have to now let j do its thing. So let's postpone saying what happens to I value. Let's start with the j value. What j should start from? Let's start from 2 to 4 here, just to have something else going on here. J starts from 2. That's the first index I have to do. What's the next thing I have to do? Well, I'm in the inner loop, so I have to carry out the inner loop first. So I have to increment j by 1, and I have to increment it 1. And when do I stop? When I reach the top limit. Okay, so that's how much j is calculated. And during that whole time, I was 1. So this is really the state, the different states that this program would do if it would be looping, doing this calculation in a nested loop. Now, when the j loop is finished, I says, okay, I can increment my counter into 2. But then the j counter starts over again, starts from 2, and then 3 and 4 again, right? It's still the same looping. So this means during all this time, my counter is I, and then that's the end of it. Because there is nothing else anymore. We have reached the upper limit for I as well. If this would be higher, then we would have to continue. Okay, so this gives me all the possible calculations I have to do. And what is it that I have to calculate? I have to calculate this expression, I plus j. It could be a totally different expression. I'm just take an example, this one, and in the homeworks you'll see different ones. So what does that mean? Well, just do the calculation for each of these, right? So I plus j, we have to, this says add the two columns, okay? Add. That is 3, 4, 5, 4, 5, 6. And what does this summation mean? Well, it's you're going to total this whole, the last column, right? So we take the total here, the sum. So this is the part that we're going to sum, right? So this 3 plus 4, 7, 12, 16, 21, 27. So that's how you calculate by hand. I'm not going to, when we do, I'm going to have you do some things like this, but there's always very small indices, ranges, so that it's like feasible to do by hand. If you do something like this, to do a calculation like going from 7 to 90, of course you can do this by hand, right? You could do this, but you're writing down basically what, 84 numbers, and you have to add all these numbers. That's going to take a little while. So that's why you don't want to do this by hand, but this is feasible by hand. Okay? This is all I want to say about this topic. As I said, I'm skipping quite a lot from the textbook. You can read all that, but I'll only assign homeworks on what I just discussed, and we will also have a little quiz on that later.